Hello all, and welcome to this webinar on using Treble for simulating listening environments. My name is Ólafur. I'm a product manager here at Treble, and I'll be your host for this session. In this session, we'll get two interesting talks from two great acousticians, Jan Olav Owren at COWI and Philip Puzalowski at audics. During the webinar, you can write your questions in the field below, and at the end of the webinar, we'll have a Q&A session to answer them. Before we begin, I'd like to thank all of those who signed up for the closed IFC beta we introduced in our last webinar. We are rolling out access to the beta in batches, and the members of the first batch should already have gotten access to it. We'll keep all of you updated as the beta progresses. We're still taking on signups for the closed beta, and at the bottom of this page, there is a sign-up form you can fill out if you're interested. We also have some other exciting features coming up, which we'll share in more detail in the coming weeks. One that I'd particularly like to highlight at this point are organizational sharing features, which we'll be launching in this quarter. More detail on that coming soon. But without further ado, I'd like to introduce our first speaker, Jan Olav Owren, who will be talking about integrating acoustic elements for optimal musical environments.
Hello, my name is Jan Olav Owren. I work as an acoustic consultant in COWI in Norway. And even though Treble is a fairly new software, we have been using it for quite some time as a collaboration partner in the early stages. So we've been doing some testing and giving feedback on user interface and workflows and desired features, etc. So it's been a really interesting and exciting journey to follow. In this presentation called Integrating Acoustic Elements for Optimal Musical Environments, I would like to present what we think Treble brings to the table as a tool for acoustic design. First, I will talk briefly about the criteria and targets for the different types of music, both rehearsal rooms and also spaces for musical performance. Then I will present a project where we have been using Treble as a calculation tool in a transformation project for a concert venue for amplified music. So firstly, I would like to just mention these two standards. So we have an international standard called ISO 23591 that covers the acoustic quality criteria for music rehearsal rooms. And also we have a Norwegian standard called NS 8178 that came out back in 2014, but the newest edition is from 2023. And this covers the acoustic quality criteria for spaces for musical performance. And NS 8178 is now also available in English from earlier this year, if anyone wants to dig deeper into this. Very short about the different needs for the different types of music. So for amplified music, you have among others the work of Nils Werner Admar Larsen, who presents that the best rated halls for rock and pop venues are the ones with the lowest reverberation time in the lower frequency area. And the worst rated halls are the ones with higher values in the bass area. For acoustic music, the relationship is different. So often the halls that are being perceived as high quality have a higher reverberation time in the bass area than in the middle frequencies. Here represented by what's called the bass ratio, and there's also other acoustic parameters showing this. For instance, the bass index. These figures are from the Norwegian standard, the NS 8178. So the green line represents the amplified music, and the red and blue ones are representing the acoustic loud and quiet music. And as you can see, you have a target for the middle frequencies depending on the size of the room. And for amplified music, you need, of course, a lower reverberation time than for acoustic music. The figures to the right shows that the relationship between the middle frequencies and the bass and treble area needs to be taken into consideration. So for acoustic music, it's beneficial to differ in the lower frequency, but that's not the case for amplified music, where you need approximately the same reverberation time in 125 Hz as in the middle frequencies, 500 and 1000. And also you need very good control in the 63 Hz band. These figures are from the ISO standard, so the same colors are applied for amplified music and acoustic music, and the same relationship is shown in the figures to the right for the relationship between the middle frequencies and the different frequency bands. So this is a case where we have a terminal building, a huge waiting area that's not being that much used anymore. So the client wanted to rebuild it into a concert venue for rock and pop music. The architect here was Mad Architecture, so the rendering in the top is stolen from them, and the pictures below shows how it used to look. As you can see, there's a lot of hard surfaces, concrete floor, a lot of glass and gypsum. And one picture is from the initial measurements, where we did some measurements of the reverberation time, how it was in an empty space, so that we could use that as to calibrate the 3D model. These are the architectural drawings of the two floors, so for how it used to look. In the ground floor you had the big waiting area, and in the first floor there was some rooms for the operating personnel, so they could stay over if they have had late shifts or very early shifts. This was the new use. So you have a stage in the ground floor to the left, a bar, toilets, an audience area, and first floor was opened so that there's mezzanine and with a bar as well on top of it. So the size of the venue is approximately 4,000 square meters. So according to the standard, that means that we should aim for a middle the reverberation time at the middle frequencies around 1 second, spanning from 0.9 to 1.1. And if we have 1 second in the middle frequencies, that means that that's the upper limit for 125 hertz, and then 1.2 will be the upper limit for the 63 hertz band. I would like to mention some work that's relevant to this topic. The first one is from my colleague Bård Stoffingsdal, who wrote a paper in 2018 on the expected sound levels at concert venues for amplified music, where a lot of concerts in Norwegian venues has been analyzed, and this dataset was then built over the next 3 years, so collecting even more data. And Morten Edvardsen wrote a thesis in 2021 on this as well. So what's interesting to see here is that, not surprisingly, but it illustrates the point that there is a lot of low frequency energy in these types of concerts. So for pop rock, jazz, etc., it's important that the venues have the acoustic qualities fitted to this spectra. In transformation projects like this case, there's a limited surfaces where you could actually do something. So here we knew that we had to apply a lot of low frequency absorption to the room. The client wanted the glass to stay because the venue is also being used as a conference place, etc. So the ceiling and the long wall shown to the right was our main surfaces to work with. And so we came up with a proposal where the ceiling was panel absorbers or membrane absorbers, thin plates spanning over a cavity, so that you get good values in the low frequency absorption area, and then adding more high frequency absorption for the side walls. So this was the initial proposal, where the wall was suggested as 24% open with a slotted panel, and 65% in one part. And here is a bit further down the road where we've been throwing this room with together with MAD architects back and forth. So here we have the different, for the ceiling, the different cavity depths represented by different colors. And yeah, as you can see, the SketchUp model and the Treble model. And then for the walls, we ended up with more 65% open space because there was need for that because of ventilation. And so we repeated that design also where there was no need, where there wasn't any ventilation behind it. So we ended up designing these cassettes that's quite simple and could be pre-built. So you have mineral wool fastened to the existing roof, and then there is this framework consisting of a cavity with different heights, and then you have a thin plywood panel in front of it. And some of these are closed and some of those are open, so that when you have them open, you could open up for more high frequency absorption, because the sound waves will then go through the open area and then be absorbed by the mineral wool in the ceiling. For the walls, it looks like this. So as mentioned, behind some of these there are ventilation, and behind some of them there's just a cavity and mineral wool, and we had to reinforce them with metal grid behind it so that it wouldn't be ruined in the first mosh pit. So here are some photographs from the final results and the opening show, and I will quickly go into the treble model where we can have a look. So here we have the wall with 65% open slotted panels and 24%. The glass, we have run this with, of course, with heavy curtains in front, as well as with the glass surfaces. The surfaces in the ceiling consist of 3 different materials representing different cavities. And in this part, because there's a limited ceiling height, we have 50 millimeters of mineral wool in this part of the ceiling. That's also because there's a bar up there, and we want to try to reduce noise from here down to the stage area as well. That's also an important aspect of these kinds of venues. So that's a quick presentation. Hopefully you found it useful, and if you have any questions, I'll be happy to answer them in the Q&A.
Thank you very much, Jan. I want to remind you that you can ask your questions in the field below, and we'll answer them at the end of the webinar. I'll now hand the ball over to Philip Puzalowski, who will give a talk about enhancing small spaces using treble.
So, hello everyone. My name is Philip Puzalowski, and I'm very happy to be here today. First of all, I would like to thank the Treble team for the invitation to present this validation study here we do in cooperation. It's the first part of the trilogy, optimizing a small room for critical listening using treble. And I'm very excited to show you the results today in this presentation and to discuss it afterwards. A few words about me. I've worked over 15 years as a live and studio sound engineer, and after study acoustic, I'm collecting a lot of experience as an acoustic engineer in different consulting companies, where I worked with different simulation software like Ease and Odeon. And since last year, in January, I've had the privilege of working extensively with Treble's Acoustic Simulation suite as a beta tester. And because I saw the potential of the software, I founded Audics, a German startup, in October last year. Audics are two acoustic engineers, Paul Sander and me, and we are specializing in audio and acoustics, particularly in soundscapes, focusing on innovative methods to shape the future of acoustic experience. We believe into a working out loud approach and collaborating with various partners in virtual acoustics, spatial audio, architecture, and office design, among others, of course, with Treble, and very exclusively together with Grana and partner engineers we are very proud of. So without further ado, let's delve into the agenda. First, I want to introduce the project and the acoustic challenges we have in such sophisticated listening rooms. Next, I will present the room, how the measurement was conducted, and the setup of the simulation. After showing the results, I want to demonstrate how critical the influence of the acoustic center is and let you listen to the impact of different loudspeaker positions. So make sure you have your headphones on. And let me introduce the project. Postscriptum Audio is a provider for professional voice productions and audiobooks, producing for publishers, media professionals, and self-publishers, from recording to editing to the finished master. And here you can see the momentary workplace. And the company plans to move into a new and smaller control room, which is now to be optimized for high acoustic standards. I used this opportunity to test simulations accuracy and compare Treble to the measurements taken in a dense grid to see how Treble can help in the planning process. And what is the challenge in small rooms? Small listening and control rooms pose a particular acoustic challenge. The aim is to achieve a reproduction that is as undistorted as possible in order to be able to evaluate it neutrally. Below the Schröder frequency, however, the frequency response at the listening position is mainly influenced by the room and not by the playback system. So wave interference in the room results in local pressure minima and maxima, whereby individual frequencies can be amplified, attenuated, or even no longer perceived at all, depending on the position of the listener and the sound source. Due to limited of space in small rooms in particular, it is helpful to know the sound pressure distribution precisely in order to position the sound source and the listening point and room acoustic measures in such a way that pressure spectrum is as flat as possible. However, evaluating the sound field often involves a great deal of measurement effort and requires a large number of measurement points. So mainly there are two wave phenomena that needs to be addressed. The first one are so-called room modes, which means the structure of the resulting sound field of the eigenfrequencies excited by the sound source, like you see on the left. And that results to the long-standing resonance below the Schröder frequency you can see in the waterfall diagram on the right. And the second one is the speaker boundary interference response, which is basically a comb filter effect. You can see here how direct sound and reflection cancel out at the listening position when the speaker is a quarter wavelength away from the wall behind it. And especially in the low end, where the loudspeaker is nearly a point source and omnidirectional, all three boundary surfaces can cause these dips. They are mainly depending on the position of the sound source, so that when you move it, you can change the response. So let's take a look on the assignment room. It has a volume of 38 cubic meters and is located on the second floor of a historic old building in Germany. The exterior walls are solid, while the interior walls are mostly made of light white construction. ceiling is divided into 3 differently designed areas. The exact structure of the construction is unknown. The floor is laminate. Some of the walls are uneven and not straight. And in order to model the angles of these walls as accurately as possible, a rough LiDAR scan with an iPhone 13 was used as a reference in SketchUp, like you can see here in the left. Here you can see the measurement setup. You can see the markings of the measuring grid with a spacing of 25 centimeters. A total of 229 points were measured at ear level. In this case, a height of 170 centimeters. The 2 ATC speakers were positioned on the shorter side of the room, forming an equilateral triangle with the measurement position at the listening spot with a side length of 130 centimeters. The mixed position is located 176 centimeters from the front wall, which is about 38% of the room length. The 38% rule is based on the research of studio designer Wes Lachlord regarding the position in the room where the frequency response in relation to the room's eigenfrequencies and low frequency interference is most balanced. And the speakers were measured simultaneously to capture the interaction and minimize the measurement effort. Additionally, the left and right sound sources were individually captured along the central axis of the room. Due to the simulation's distance restrictions from source 1 and 2, 28 positions near the sources were omitted, leading to a total of 201 receiver points versus 229 measurements. Regarding room modes and interaction with boundary surfaces, the frequency range of 20 to 300 Hertz is primarily in focus. Thus, only the woofer was approximated with an omnidirectional sound source. And because of not exactly known room acoustic properties of the walls, the old windows and door, the input data of the simulation was calibrated to the reverberation time at the listening position. The plots of EDT, T20 and T30 for both left and right speakers at the listening position show a very good match between the simulation and the measurement. Slight difference in the mid-range between 500 and 1000 Hertz suggests that the room stamping in this spectrum was slightly underestimated. The difference below the Schroeder frequency are explained in the spectrogram. Here you can see that the temporal behavior of the room in the simulation is captured very well, except the decay at 109 and here the 147 Hertz. See here this difference. And I suspect a resonance in the plasterboard wall, which I could not model sufficiently due to the limitation of the input of the material properties. So you just can enter in octave bands. And here you can finally see the frequency responses, which indicate a very high match for both sides. The deviations on the right side at 60 Hertz are also likely due to the material modeling. The 100 to 140 Hertz range is mainly affected by the interference, as we will see later. For the validation over the entire measured area, the impulse responses from the simulation of both sources were summed using a Python script, and together with the impulses from the measurement, transformed into the frequency domain using an FFT with a resolution of 0.5 Hertz. The SPL values were normalized, and all data is displayed as a heat map over the area of the room. The room modes in the simulation appear very similar to the measurement. There's a frequency shift of 1 Hz, slight local shifts between measurement and simulation of the modes on the grid are partly due to inaccuracies in the placement of the measurement positions in the real room, and also due to irregular and uneven walls. I've prepared this here for this presentation as a film so that you can see all frequencies in one run. It starts below the first room mode, which is 36 Hertz, and mixing position is here row G, column 7. So I will start it now. And here you can see that it's matched very nicely, special until 100. And then you can see here's the frequency running up to 200 Hertz. And I think that's the last frequency below the Schrödinger frequency. You can see that nice match here. And I also want to show you the influence of the acoustic center on the speaker boundary interference response. The manufacturer specifies the acoustic center of the speaker to be in the middle of the mid-range driver, as shown on the left. Finally, the position of the point source in the simulation was a little bit above the center of the woofer, as shown on the right, to have the best match about the entire area. So it's a compromise because of the limitation of modeling the enclosure of the loudspeaker. The impact of the position on the transfer function is demonstrated on the left with 9 source positions in a grid with a spacing of just 10 centimeters. On the right, you can see the resulting frequency responses. And you can see the peak at 109 Hertz, where the second axial mode of the room's width and the third axial mode of its length, point side, varies up to 26 dB within the displayed arrangement, depending on how it overlaps with the interference from the first reflection. The difference between mode and reflection can be recognized by the fact that the frequency of the latter changes with the position, particularly here in the 100 to 140 range. You see the dip is moving to the left from here to here to here to here. And you can also see the same phenomena here in the range from 160 to 200 Hertz. And it's very impressive that due to wave-based and frequency accurate analysis with Treble, this phenomena can be identified and addressed already in the planning stage using a commercial room acoustic simulation software. Finally, I want to demonstrate that these differences are audible. So please put on your headphones and let's jump into the auralization. You will hear a floor tom sample tuned to 110 Hertz, so an A. I use a transient sample so that the effect is audible for everyone. Please be careful and do not turn up the volume when listening to the dry sample. This is much quieter than in the room. And in the frequency plot on the left, you can see that the highest peak is achieved at position 3 and the lowest peak at position 8, where the reflection hits the mode the hardest. So let's start the auralization. You see here the receiver and the arrangement of the sources. In the middle is number 1, and the others are arranged around in a 10 centimeter grid. You see here the mixing channels in the auralizer. We will hear source 8, where the room is pressed the most, source 3 where you can hear the full resonance and number 1 chosen in the simulation. So I'm starting the sample. And now it's getting loud. Exactly. I will turn around so you can hear the speciality of the auralization. So now you can hear the resonance clearly. Now it's gone. It's the lowest peak. And back, and you hear clearly the resonance standing in the room. Yes, exactly. In summary, it's really exciting to have the possibility to measure in a virtual twin and to understand the acoustic in the room with Treble. On the one hand, through the frequency accurate analysis, and on the other hand, through the direct listening into the room. And of course, there are still limitations, but the accuracy with which the results are presented are really very impressive. I'm currently working on the design, but I don't want to reveal anything yet. Of course, we are particularly excited about the final measurement with the final treatment. We also want to publish all the results, so stay tuned. And then I think we will get to the Q&A part, and thank you very much.
Thank you very much, Philip, for this very interesting presentation. We will now transition into the Q&A session of this webinar. And I remind you that we have a form open here in the field below where you can still ask all your questions, and we will do our best to answer them. Now, we have already gotten a few questions related to Jan's model and results that relate to the results and how the absorbers were modeled. So I'd like to start by handing it up to Jan. If you could talk in a bit more detail about your results, that would be very interesting to hear.
Sure. I think I'll try to share my screen so we can go into the model. Hopefully I'm doing it now. So in this, I have several editions of this room, but here, let's see what we have. So if you remember, we wanted the result in the middle frequencies to be around 0.9 to 1 second. And that's what we got. And for this result, when we have curtains in front of all the glass surfaces, it's quite flat down to 125, but as you can see, it shoots up to 1.5 in the 63 hertz band. But that doesn't, I'm not too nervous about it because the initial measurements did not have that much reverberation time in the 63 hertz band because of the glass acting more like a low frequency absorber. So if you compare it without curtains, you will actually see that it drops. And the reason for this is because in the materials that's used, so the curtains, the lab data is with probably a concrete surface behind it. So yeah, these results looks quite similar to the final measurements.
And when modeling the membrane absorbers and the absorption data for the membrane absorbers, did you use your experience, or what did you?
Yeah, so there's some in the program. There are some materials that are that you can use as a starting point, but also we have data and calculations from our own measurements, and also using software, for instance, NoFlag or WinFlag. And Zorba is also a software where you can calculate the theoretically resonant frequency for those kinds of absorbers. But yeah, they are tuned to work in the low frequency area from 125 hertz and down to 50, if I remember correctly.
Yeah, I can add to that in the near future, we would like to add something similar to those softwares you've mentioned into the tool itself, so that you can build your own absorber with layers and different materials, just using Treble.
Yeah, that's a great feature.
That is something we are starting work on very soon. There was a question also about the area below 63 hertz. So currently we model down to the, or we allow the input of absorption data down to the octave band centered around 63 hertz. That's a hard limit in the current iteration of the software. I would say the next step would be to allow for 1/3 octave bands, and then we would probably go down to 50 hertz with regards to input data. That's kind of the direction we're looking at right now with that regard. Oh, let me see here. Please keep the questions coming. There is a question here about room modes. How is Treble taking into account room modes? Is there a way to simulate suppressing room modes with absorbers? And I can answer this question. So the way the Treble works is that we have two solvers. We have a wave solver and a geometrical acoustical solver. And the wave solver solves the wave equation directly. So it inherently takes into account and calculates all the room modes in the room. And you can, for example, see the frequency response in the room in our result view and see how the model behavior of the room affects the results of the simulations. Here's another question for Jan. The layout at the ceiling makes it look like you simulated different pressure zone with surface receivers. Did you use surface receivers during your
No,
simulation?
not in this. I haven't used it in this project, no.
No.
It's only point receivers.
Yeah. What we do allow is that you can have a surface receiver grid that you can use to get the overview of the behavior of the entire room. You can also have individual point receivers, and you can multi-select the receivers to get kind of an average across all the receivers that you define. Now, if I hand the ball over to Philip a little bit, I think this is a very interesting and good presentation. Well, here we have a question even. For Philip, you mentioned the study was available publicly. Where could I find it?
Good question. The study is you can find in the insights of the Treble homepage, and probably we go to Internoise with the study also. Yes, but mainly you can find it in the insights of the Treble homepage. Yes.
Yeah, and we will post a link to the page in the chat. And there is another question, will this webinar be available online to review the second time? Yes, we will send a link out to all the attendees, for all those who signed up to the webinar, and you can watch it at your own leisure. But getting back to Philip, how has this kind of, if you talk a bit in general terms, how was your workflow kind of in these projects before Treble? And how has it kind of changed by using Treble, if you just talk very generally?
Yes, before Treble, when you want to get in this detail to know what's going on in the room with the room modes and the boundary interference, we do a lot of measurements, and that now you can now you have a virtual twin. You can move your sources, you can move your absorbers and test it every 10 centimeters without getting off your chair. And that's very fine. And yes, that's the workflow at the moment. You can test so many variations without moving absorbers in the room, and that's great. Yes.
Yeah, that's great to hear. And I think kind of improvements we would like to make in the very near future to make life easier and better, of course, as we always want to do in these cases, is first, we would like other people or our users to be able to sum sources in our tool directly.
Yes.
That is kind of the #1 priority with regards to all of this.
Mm-hmm.
And also to kind of be able to visualize the model behavior of the room. And you had these very nice presentations, the video that you put up, so that you could have something like that within the app itself.
Yes. Yes, we're waiting all.
Yeah, that will happen very soon.
Yeah, very
So
cool. Yes.
that'll be exciting when that feature will launch. If we go back to Jan again, no, sorry, there's a question for Philip. Did you add treatment to the control room? Did you simulate the effect of absorption, and how did you match them to the measured results?
Yes, in the first step, to match the measurement results, yes, I calibrated the simulation like with every other simulation you do it. You calibrate the absorption coefficient and check if you match with the reverberation time. And we are at the moment I'm working on the design, so on the treatment, and yes, and you can certainly simulate the effect of absorption, and yes, you can test many configuration of absorption, many position, and yes, you see it in you can download the impulse response, you can use it like you measure in the real room. That's the way I use Treble.
Yes. There's another question here. Can you import source directivity to our source in Treble? We do allow the import of CLF files, directivity files from loudspeaker manufacturers, where you can take that into account. Currently, that only works for the geometrical solver. We are working on the backend on kind of implementing a solution to add directivity to the wave-based solver. We have actually come up with a method to do that, but we then just have to implement it into the tool. Here's another question for Philip. Philip mentioned the difficulty in entering data only in octaband. Will you implement more or this is from me actually, will you implement more tools for inputting material or 1/3 input data soon? Yes, that is on the roadmap. I currently don't have a release date for it, but it is absolutely something that we will do. And another question, can we simulate or oralize different reverberation times? For example, RT of 300 milliseconds or 500 or 1 second. Yes, you can run different simulations and run an oralization for each of them. So the kind of the reverberation time is not a limit on the oral session, if I understand the question correctly. Now, if I go over to Jan again, when you're working with this ISO standard for practicing halls for music and performance halls, how do you kind of balance when you have, for example, a hall that has a fixed size, and then the client wants to have some performance there that might not be the best case for that hall? For example, if you have a really big brass band in a really small hall.
Yeah, that's a very relevant question. It's a never-ending question. So I guess that the answer is that you have to try to make the client understand what they are getting, what they are ordering, and it's not like a rehearsal room for a brass band is completely useless for other types of music, but it's not optimal, and that's important information to give. But we are working now a lot with these AAS systems, so yeah, artificial reverberation time, they're popping up in many places in Norway, so it's exciting technology that's going to keep on evolving.
Yeah, that's very exciting. Another question here: what is the frequency upper limit in general? Depends on the room size or mass or comp power. Well, the upper limit is the octave band centered around 8K currently. And then if you're using the wave solver, then the higher you take the wave solver, and generally then the more computationally heavy the calculations become, because the way the wave solver works is that it creates a mesh, and the fineness of the mesh is based on the transition frequency. That is the frequency you transition between the wave solver and the geometrical solver. And the higher the transition frequency, the finer the mesh, the more detail you have to add into the room, and then the longer the computation time becomes. So it is this kind of balance. That is why we have the two solvers, so that you can set the transition frequency appropriately for each case and can balance this kind of computational time versus accuracy. And there is a question for Jan. What is the name of the company that does artificial venue reverb extension?
And there's now several types of vendors. So there's Maya Constellations, and Yamaha has their system, Siap, Amadeus, etc.
Yeah. If you have any more questions, please keep them coming.
Just to follow up on the transition frequency, you can mention that Treble does that for you as well. The program suggests transition frequency.
Yeah. And that suggestion is based on the Schroeder's frequency.
Yeah.
Below which the model behavior is expected to be dominant. And we have some guidelines, and we are adding in guidelines on kind of best practices when setting up a model in Treble. Because that is an important point to touch on, that, for example, those of you who are used to working with geometrical solvers, then the kind of detail in the model is often appropriated by the use of scattering. So you have, for example, a higher scattering coefficient for a surface where you exclude a lot of detail. A very common example of that is when you're modeling audience area. In some softwares, you can model it just as a box and then have a very high scattering. So you kind of use the scattering instead of drawing in geometrical detail. But scattering is purely a geometrical acoustical concept in the context of these solvers. So what the wave solver itself sees as boundary conditions is just the geometry that is actually modeled. So it's very important that as you go up with the wave solver, as the transition frequency increases, you have to draw more detail, geometrical detail into the model, get a realistic representation of how the wave front progresses within the room in question. And a rule of thumb on that is to model detail down to approximately quarter wavelength of the frequency you set as your transition frequency. And we have written a document about that, which will go live on our documentation page this week, actually. So that's one of the nuances of working with Treble, is that the wave solver behaves a bit differently than geometrical solvers do in terms of inputs in that regard. So to get good simulation results, you have to keep those things in mind. And that will be documented, as I say, on our website coming this week. Let's see. I guess for Philip, you will be having a talk on internoise on this exact setup. Is that a correct understanding?
Yes, we submit the paper, yes, and I hope it will work. Yes, I think we are on the internoise.
Yep.
With this paper, yes.
Yeah.
And we're very proud of it, yes.
Yeah, be exciting to see. And then a question for Jan. How did you use scattering to match high frequency to measurements, or did you mostly tune the absorption coefficients?
Yeah, so the main focus has been in the lower end of the frequencies. So I don't have the model in front of me now, but I think the transition frequency was around 200 hertz suggested by the software itself, which is it 4 times the Schroeder frequency or something like that?
Yeah, approximately. That's approximately how we set the transition.
And it probably fits, because then you need to have an estimate of the reverberation time before you have it.
Yeah.
And this being, is it 1 second in the software? Or?
The initial estimation is usually is based on Sabine, and then I am actually I think the estimation is based on Sabine to get the Schroeder's frequency. And now you can also, it was previously not possible, you can see the result of the Sabine calculation as you set up the model. So you can have that in front of you. And do you have any more questions? Again, then, if I can ask Philip, just coming from like a personal experience, I'm very impressed with the kind of depth of the measurement detail that you went into and made like this great case for your client. Can you explain to us in a little more detail kind of what the client wishes were going into this project?
Okay. Yes, of course. Yes. The thing is that the room is very small, but I think in a floor area of 14 or 15 quadrat meters, and the guidelines don't fit really. It's a little bit too small for the guidelines, but we want to how do you say along the guidelines. So we orientate on the guidelines, but you can't really fit this goals because it's a little bit too small, the room. But I think I think we can get the overall reverberation time to 0.2 seconds, something like that. And the goal is also to tame the room modes to this decay time also. We have to look at what it's possible, but that's the goal we want to achieve. Yes.
And as you mentioned earlier, work is kind of progressing on that front right now.
Yes, we are working on that. It's a little bit the thing we want to do it completely with Treble. It's for us. It's also a little bit a research study, and we want to use the features that are coming, and so it's a little bit in a parking position. As we wait a little bit at the moment, but we also are testing already with porous absorbers. What you can do in the room, how much absorbers you need, and so on. And you can already say a lot about this, and you can also see where the points are, where the first reflections hitting the listening position, and yes, that you can also see already see in the simulation. And but yes, we want to also use some or want to see what happens with resonant absorbers in this room, and yes, and so we are waiting at the moment.
Yeah, thank you. There's another question. Will the event be available to view on demand? Yes, we will send a link to everyone who signed up. I want to piggyback a little bit and kind of extend my answer on kind of the material generator that we kind of want to implement. And that is the fact that there is this difference between the absorption data that you get, this statistical data that you get from these reverberation chambers that manufacturers often provide, that can be influenced by both the room itself, the model behavior in the room itself, and then kind of diffraction about around the kind of measurement setup. And that is fine for kind of energy-based calculations, such as geometrical solvers. But the wave solver we employ, and also the wave solver we employ, is pressure-based, and kind of the best input data for that are absorption coefficients based on measurement of impedance derived from flow resistivity. They're more realistic and are not influenced by the room itself as much. And that is the data we have in our material database, is based on these factors, and usually provide better results, especially, of course, in the low frequency range. When you measure in a reverberation chamber, you can sometimes get a bit unrealistically high absorption at low frequencies, and even in high frequency, as most of you know, you can get cases where you have absorption above 1, for example, in the most extreme cases. And kind of this is one of the chief motivators behind having a sort of a material generator within our tool that can directly confront this issue or this fact. Now, another question to specify, could we input acoustic impedance directly at some point? Yes, absolutely, that would be a part of it. We actually have another solution which is not open to the public, which is called the SDK, the Software Development Kit, which is a programmable interface towards using treble. And in that solution, you can actually import impedance directly. So we have the technology and we are currently doing it on our end. The only thing we have yet to integrate is to basically put it in the tool itself and the user interface around it. So that will be coming in the near future, absolutely. Now, if there are no more questions, I think we can conclude this session. Thank you very much, Jan and Philip. Two very interesting talks.
Thank you.
Did a great
Thank you.
job, both of you. And as stated, the link to the webinar will be sent out to everyone who signed up, so you can watch it at your own leisure. But stay tuned for future updates from our tool, and thank you very much for attending this webinar.